Alright, so I just got done talking about starting and creating arrays. And I was going to go into a little bit more about matrices and so forth, but I'm going to save that for the next couple videos. Right now what I want to get to is doing some more functions in MATLAB. We've got some groundwork on how to create arrays, so let's use them more creatively with the functions and how that's going to work. But first and foremost, before we can get into that, you got a little sense of how MATLAB displays numbers. And how can we enter in values that are more complex numbers? So, for example, if I was going to enter in Avogadro's number, we can call it NA, I can say 6.02 and e to the 23rd, just like in Excel, and we'll get that as our output. Note, and it's important here, that if you're going to use the E notation, by entering it in an E, it outputs in that E notation, which is nice. But if I put a space here and hit enter, it's going to get upset with us. It's not going to view this as a valid argument. It doesn't know what that expression is. It's unexpected in MATLAB. It doesn't like that input. So realize, be very careful with your spacing on this, because you don't want it to, that it has to be all one combined term. Otherwise MATLAB won't know how to deal with that value. So with that said, the other thing you can do, and the other thing you can think about, is looking at how you can format outputs in Excel. Now, or in MATLAB. Now note, MATLAB will always deal with numbers as double precision floating point numbers, meaning it'll always be these large complex real numbers in there. But even if it's outputting as an integer or other, it's going to deal with it as a floating point number. But there are other formats you can look at and display. So if I said help format, this gives you an idea of the kind of number of formats that can be outputted. Here you'll get a sense of short, long, short E with floating point precision, long E. These just gives you a sense of the different kinds of format that MATLAB can put out. Normally the short is the format that you normally see is scaled fixed point with 5. If you have numbers that are varying across a wide range, you may want to put the floating point or the engineering setup as your default option, because these will be the ones that is what it will look like in its output. So keep that in mind as well. These are very useful tools. So if you want, you can actually move to format short E, and now if we ever did anything like NA, it shows you the display and the output that it's format that we've requested of it. So this is just a quick format change that you can make in Excel or in MATLAB to make it clear. So with all of that said, just like Excel, MATLAB has a whole bunch of built-in functions available to you. And I'm going to have a companion PowerPoint slide put up in the documents that goes along with this. So I'm not going to cover all of them here, but I will try to cover a lot of them that you have. From elementary math functions, trigonometric functions, data analysis, which is extremely important, obviously, complex numbers, computational limits, and so forth. So these are all powers that we have within MATLAB. So from an elementary function, things like square root, sine, cosine, log, all of these things we have built in trigonometric functions and so forth. So if I said clear CLC, and I went ahead and created a array. Let me create a vector, and I'll create a vector called data, and this data is going to be 1 to let's say in increments of 0.4 to 100. Okay, so we'll have a fairly large array of 248 spaces. Now, if I said the sign of data, and I create this, hit enter, and we get these columns, I'm going to actually redisplay that as a row column vector so you can see what that looks like. But you'll see it took the sign of every individual point individually in that function. So it's actually taking that array in and calculating that function on each point independently, which is a nice way to look at this. You can do the same thing for square root. You can say, if I said the square root of your data, and put the little apostrophe to push it into a column, again, you see this. If I didn't put that apostrophe, it'll just be column format. It'll be row format instead of column. But you can see again, you're just doing that large calculations across this entire data set. If you didn't know what was happening with that, you can always say clear and CLC, and I can say help on the square root, and you can get a sense of what the square root number is doing. So that's a good point to look at. There are some other elementary math functions that you can do in Excel, I mean in MATLAB as well. I'm going to say Excel continuously, so just pretend every time I say Excel from now on is probably, I mean MATLAB. I'll try not to do that. But the thing I can do here is, importantly, elementary math functions, the other ones that exist, you can take the absolute symbol. So instead of having numbers, let's say I said data was equal to -5, 1, 5. Okay, and we get this nice uniform values. If I say absolute value, ABS of data, it's just going to take, obviously, the absolute value of those ranges. Similarly, if I said sign of data, that is going to distribute and present the sign of the value. Seems a little weird, but it's showing here that all these were negatives, and it just turns it into a -1. This was 0 because no sign, and that was 1s. So that just gives you the sign of the value. You can also say exponential, and it's the exact same function as in MATLAB. I can say data, and you're going to get the exponential of those values. Interestingly, and I'm going to point this out, unlike, I think it was different in Excel, I'm now trying to remember, but log is the function for ln. ln is not ln. There is no ln. If I say ln of data, it's undefined, does not exist. Log, however, is actually the natural log. It is not the log base 10. If I want log base 10, it's log 10 of data. And then you get that. And that's it. You'll notice, though, if I say log data and enter, so and you have that ability. So CLC help log, and that'll give you obviously the other forms you can see. You can say the different logs exist: logs 2, log 10, log m. If I click log n is a matrix log, and it returns the matrix log from that system. So you can see that you can learn a lot from just kind of doing some help files and doing some searches from that. So again, the function inputs can often be scalars or matrices, and most of the functions are built where you put them in. Unless it's a matrix function, it's going to treat it as an array, meaning each independent element is going to be handled independently. And these are very important points. So to start with, let's consider an example where, and I'm going to go through this example that we have actually in this PowerPoint slides, and we'll go through this step by step. So I'm going to bring this slide over into the window so you can see what it is that we're talking about and go from here. So the problem statement that we're going to be operating with is this. We're going to be calculating values with arrays, calculations on functions with arrays. And the problem statement is we're going to look at the saturated vapor pressure of water that can be determined using Clausius-Clapeyron equation for the following system, where the equations are given below, where P sat is saturation vapor pressure in millibar at T, and delta H is our latent heat of vaporization for water. And we're going to set that as a constant at 44 kilojoules per mole. And so what we're going to really want to find out is determine the vapor pressure of water from -60 to 120 degrees Fahrenheit in increments of 10. So that is going to be the problem that we are working with. And we're going to do this actually in our M file. So I'm going to go over to our M file, and we're going to create a new M file. Actually, what we'll do, let's create a whole new file. And so this one we are going to look at and create an M file called our Clausius Clapeyron. I'm probably misspelling this entirely. I'm forgetting the Y. Equation to find set vapor pressure for water at different temperatures. All right. I intentionally typed that out because I wanted you to see what happened. If you notice, when I went over to this line here, there's this very faint line. You might not see it in YouTube, but yeah, this very faint line. The moment I hit that line, it automatically went to the next line. Since I was typing a comment, it instantly assumed I was making a comment. So I put a percent symbol at the beginning and it kept that comment going. So that's kind of a nice little feature here. So at the beginning of this file, I'm going to say, because I want everything to start cleanly, so I'm going to say clear CLC. I can keep them as two separate lines, or I can put them on one line with a comma. That's going to give them as two separate commands, and enter, and we have that. So the first thing we want to do is actually define the temperature of our system, and we're going to define this in degrees F, right? So in Fahrenheit, because that's the problem set that we have. So we were looking from negative 60 degrees Fahrenheit to 120 degrees Fahrenheit in increments of 10. So I'm going to put in between these values 10 because that's the increments we want. And I foolishly put them in parentheses. It's not parentheses. We actually want this in the brackets. So we're going to put a semicolon at the end, and we're just going to define this. We're saying define temp matrix or temp vector in the not micro, degrees Fahrenheit. There we go. And to type that in, I actually, if you remember, it's Alt 0186 gives you a degree symbol. So you hold down the Alt key, go to your number key, type in 0186, let go, and you'll get the degree symbol. So we're going to create a vector that's going to calculate temperature in Kelvin based upon the temperature in Fahrenheit. So we're going to have to physically convert this. So it's TF plus 459.6 divided by 1.8. This is just the unit conversion on this. This first one, value here, add 459.6 to convert Fahrenheit to Rankine, and then divide by 1.8 to convert Rankine to Kelvin. And enter. And again, we're going to define this as saying convert temp to K to give us our Kelvin, not degree Kelvin, but just Kelvins. Next, we're going to put in our heat of vaporization. Delta H is equal to 44100, and that's latent heat of vape in units of joules per mole. All right. And then finally, we have our Avogadro's, or our ideal gas constant, which is equal to 8.314. And that is ideal gas. And the units here are going to be joules per mole per Kelvin. Lovely. So now we can actually do our calculations. So the first thing we want to say is we're going to calculate the vapor pressure. Vapor pressures. And vapor pressure is equal to 6.11. Now you can go to your equation to confirm this, to confirm this, and that would be a good experience. But you can say to the exponential, because we had in the equation ln, so we had to take the exponential both sides. Ln of our exponential of delta H divided by R. R is a constant now. Now remember, R is a scalar, so we don't have to put a dot there. But in this case, I'm going to, because it doesn't really matter. But if it was R was a vector or an array, and we wanted to do that, we could put that in. Times 1 divided by 273 minus 1 dot divided by TK. Close all those off in parentheses. And because I get really nervous, in truth, you don't need a dot here, and you don't need a dot here because of the way the value, well, you don't think you need a dot there, but I'm never 100% certain, so I'm putting a dot in there. So just in case. And I think we'll be safe that way. And then we can next look at and display my results as a table. So we can actually take this value. This is all we had to do. This was vapor pressure. This is what we wanted. But perhaps we wanted to have a table of this result. So we can say my results will equal to, and we'll say TF, because we want it in Fahrenheit, to vapor pressure. Now you notice these are all row vectors, and I'm going to use the invert transpose symbol to transpose this to a column, comma, vapor pressure, transpose, and we have that. I don't type result. I don't know what that is. Let's fix that. Results. And so we have that, and we can display that as a result. And then finally, we can also do plot vapor pressure as function of temp, and plot TF vapor pressure. Now I'm going to double check everything really quickly. I'm going to hover over to make sure, yep, vapor pressure is all here, it's all defined correctly. I'm going to hover over, and yep, TF seems to be defined properly. TK, yep, we have that one. Delta H, yep, we have that. So I think everything's good. So I am going to save this, save, and we'll just call this the vapor example. Now note here we are using temp plot. We are going to talk a lot more about plot later and how you can make it look pretty. But for this time being, we're just going to hit run, and sure enough, we get a plot where our X value, which was unlabeled, is our temperature, and our Y value is our vapor pressure, which is again unlabeled. And then over here is our table that was created that shows all this in results. So bring this back up, and oops, too big. Come on, close. Okay, there we go. Now, that is, in a nutshell, the entire way you would actually do another problem, and how you can do these complex values with arrays instead of arrays or vectors instead of single value scalar problems. And it's a great example of this kind of work. So I'm going to continue on and give some other additional examples and just kind of forge ahead a little bit. Note that there are some other things we can do in there. We have things like discrete mathematics, where we can actually find the prime numbers, we can find prime factors, we can find greatest common denominator, lowest common denominator, we can get factorial of numbers and so forth. So if we wanted to say 5, if we had a, let's say we had an array, let's clear everything and start over fresh, and I'm going to say data is equal to 1 to 5, and I said factorial of data, we would get the factorial of that, which is here 5 times 4 times 3 times 2 times 1, 4 times that, and so forth. We could say factor of data, and must be a scalar, so you must put in as a scalar. This is a good example. So here we can actually say factor of 500, and it gives you the factors that are used to prime factors of x, as you know. And the greatest common denominator, you can also find least common multiple and so forth. There's a lot of things that are built into it in the discrete mathematics world. A lot of trigonometric functions. You can actually find your arc sine, inverse sine, hyperbolic sine. All of these things exist, again, just like in Excel, and so forth. You also have the some functions can actually give you more than one value, more than one output. Now this gets a little interesting. So for example, clear, let's do CLC. There is a function called size. It's a very useful one in that it gives you the size of the array that you're working with. So let's say I said CLC, and I'm going to create a function or a data array of 1, 2, 3, 4, 5, 6, 7, 1, 4, 2, 2, yeah, there we go. And we have this matrix. I can say, if I said size of data, it would say 4, 3. You'll notice it outputted 2 separate numbers. I can actually have and use those numbers as an inputs to 2 separate variables by the assignment operator. What do I mean by that? I can say, by using brackets, because you can think of this as creating a vector or an array, I can say rows, comma, columns. So I have these values, rows and columns. I'm defining a vector called that, which is going to then equal to the size of data. Oops. Data. And then so doing, I've now just turned my answer 4 into a thing called rows and column as a thing called 3. There are some examples where if you don't actually define this output, you'll only see one value and you won't see the other information. And you'll learn that in the actual description of the vector that you have. A lot of this is actually this is actually very useful in the terms of identifying. This is very useful in identifying when we get to mesh grid, we get to more complex functions. You can always look into the help file to see which of these functions are going to fall prey to this problem or not. So just realize that that does exist as a problem. Because this section is going on a little bit long, I'm going to pause here and continue this discussion in a following video. All right.